Hello students, in my previous lectures, I have discussed with you the theory of homogeneous linear system dx by dt is equal to atx, where x is an n cross 1 column vector and at is an n cross n matrix where the entries of the matrix are assumed to be continuous on some given interval ab. There we studied the concept of solution of system of equations. Then we introduced the term Wronskian of n-vector functions. With the help of Wronskian, we obtain the linear dependence and independence of solutions. And then we made a fundamental set of solutions of the system. The fundamental set of solutions, beside being the solution of the system, is also a set consisting of linearly independent vectors. And then we obtain the existence theorem for the fundamental set of solution for dx by dt is equal to atx. And we also proved that a linear combination of the solutions is also a solution, and any arbitrary solution can be written as linear combination of fundamental set of solutions. Then we obtained very important formula, namely Abel-Liouville formula, expressing Wronskian in term of Wronskian at a point and some expression involving trace of the matrix AT. After that, with the help of the basic theory of homogeneous linear system, we derived the theory of non-homogeneous linear system. In this lecture, I am going to discuss the theory of nth order homogeneous linear differential equation. Since we know that corresponding to a single nth order homogeneous linear differential equation, we can obtain a system of n homogeneous linear differential equations. Thus, both the theories, that is, theory of the system of n homogeneous linear differential equation and the theory of single nth order homogeneous linear differential equation, they are dependent on each other. So, with the help of the results obtained in the theory of linear homogeneous differential equations, we will derive theory of nth order homogeneous linear differential equation. So let's start the theory of nth order homogeneous linear differential equation. First, how the nth order homogeneous linear differential equation looks like. The most general nth order differential equation is given by equation 1, in which derivative of nth order appears. Since we are saying it is of nth order, thus the leading coefficient, namely a0t, must be non-zero on the given interval. Throughout this section, we assume that the coefficient a0, a1, an of nth order differential equation 1 are continuous on some given interval ab. Now, to write this equation in more compact form, sometimes in this section we will use the operator notation given by ln x is equal to 0, where the operator ln is defined by a0t dn by dtn plus a1t dn minus 1 by dtn minus 1 plus so on up to ant. The nth order differential equation 1 is said to be normalized if the leading coefficient of this equation is 1. And we can always make equation 1 normalized by dividing throughout the equation by a0t. We can divide by a0t because we know that a0t is not equal to 0 throughout the given interval. And now we will start the theory of nth order homogeneous linear differential equation with the statement of existence and uniqueness theorem for nth order homogeneous linear differential equation. The existence and uniqueness theorem for nth order homogeneous linear differential equation. The statement is as follows. Given any nth order homogeneous linear differential equation of the form 1, where we are assuming that the coefficients a0, a1, a2, an all are continuous on the interval ab, and the leading coefficient a0 is non-zero throughout the interval ab. Take t0 to be any point of the interval ab and c0, c1, c2, cn minus 1 be a set of n real constants. Then the existence and uniqueness theorem says that there exists a unique solution phi of the equation 1 satisfying the condition that phi at the point t0 is c0, phi dash at the point t0 is c1, and phi nth minus n minus 1 derivative at t0 is cn minus 1 over ab. And here we are not proving this theorem, we are just taking the statement of this theorem, and with the help of this theorem we will prove the corollary of the theorem. And the corollary says that if phi is any solution of the equation 1 such that phi at t0 is equal to 0, phi dash at t0 is 0, phi n minus 1 derivative at t0 is 0, where t0 is any point in the interval on which the coefficients a0, a1, an are all continuous and leading coefficient is non-zero throughout the interval, then this solution phi must be 0. The proof of corollary is very simple. Now for the proof, you can see that phi t is equal to 0 is always a solution of this homogeneous linear differential equation 1. And phi t is equal to 0 also satisfies the condition that phi at t0 is 0, phi first derivative at t0 is 0, phi n minus 1th derivative at t0 is 0. So now if we use the existence and uniqueness theorem, which says that if there is any point in the interval ab and for any set of real constants there exists a unique solution. The solution must be unique, satisfying the condition. Now, since we have taken the solution phi t to be 0 and the condition phi t0 is equal to 0, phi dash t0 is equal to 0, phi n minus 1th derivative at t0 is equal to 0 is satisfied if we take c0, c1, c2, cn minus 1 all to be 0. So all the conditions, or you can say all the requirements of the theorem are satisfied, and with the help of this uniqueness theorem we will get that there is one and only one solution, and you have already prove that this phi t is equal to 0 is a solution. So the only solution is phi t is equal to 0. Therefore phi t is equal to 0 for all t in AB whenever phi is a solution and phi satisfies the condition that phi at t0 is equal to 0, phi dash at t0 is equal to 0, phi n minus 1 derivative at t0 is equal to 0 for some point t0 in the interval AB. So before moving further, First, recall that corresponding to the nth order homogeneous linear scalar differential equation, there is a linear system of n differential equations. Thus, corresponding to equation 1, we can always find a system of n differential equations. If we take x is equal to x1 and dx1 by dt is equal to x2, dx2 by dt is equal to x3, and dxn minus 1 by dt is equal to xn, and we substitute these in equation 1, we get dxn by dt is equal to minus ant over a naught t x1 minus an minus 1t over a naught t into x2 minus up to minus a1t over a naught t xn. We call this system of n equations as 2. And this system further can be written in the vector differential equation as dx by dt is equal to atx, and we name it 3, where the vector x is an n cross 1 column vector having the components x1, x2 up to xn, and the matrix A is an n cross n matrix whose second element of first row is 1 and all the remaining elements are 0. In the second row, we have only third entry as 1 and the remaining entries of the second row are also 0. And in the n minus 1th row, the nth entry is 1, all other entries are 0, and from the last equation of the system we made, we get the nth row of this matrix is minus an by a naught minus an minus 1 by a naught up to minus a1 by a naught. And the equation 3, sometimes called companion vector equation of the nth order scalar equation 1. From now onwards, we use this equation 1 as a standard equation of nth order homogeneous differential equation, and its corresponding system of n equations will be given by 2. In our next result, we will prove the dependence of solution of the nth order equation on the solution of the system, and conversely. So moving to our next result, if f is a solution of differential equation 1 on interval AB, then phi given by a column vector whose first component is f, second is f dash, and nth component is the n minus 1 derivative of f, is a solution of 2. That is, we can derive the solution of the system from the solution of the nth order differential equation. And conversely, if phi given by a column vector phi1, phi2, phi-n is a solution of the system 2, then its first component, namely phi1, will be a solution of the nth order differential equation, and we denote the solution of nth order differential equation by f. And if we further notice, then this phi given by phi1, phi2, phi-n will be of the form f dash up to f n minus 1 derivative. So let's start the proof. Now given f is a solution of the nth order differential equation, so we need to prove that phi given by f, f dash and f n minus 1 derivative will be a solution of 2. Now because f is a solution of differential equation 1, therefore f will satisfy 1. And when we substitute, we name this equation by A. Then we take phi t to be ft f dash t up to f n minus 1 a derivative at t. Now we will prove this phi is a solution of the corresponding system of equations to 1. We name this phi t, which is equal to ft, f dash t and so on up to f n minus 1 t, which we again taken as the component phi 1 t, phi 2 t and phi n t as b. Now from b, if we equate the corresponding entries of both the column vectors, we get phi 1 t is equal to ft. Similarly, equating second entry, we get phi 2t is equal to f dash t. But from the previous equation, we get that this f dash t is equal to phi 1 dash t. And similarly, phi 3t is equal to f double dash t. And from the previous one, we get this f double dash t is equal to phi 2 dash t. And similarly, moving in the same manner, we get that phi n minus 1 t is equal to f n minus 2 a derivative, which is equal to phi dash n minus 2t. And from the last entry, we get that phi nt is equal to f n minus 1 a derivative, which is equal to, from the previous equation, phi dash n minus 1t. And now we name these equations as C. If we differentiate the last equation obtained in C, we get that phi dash and t is equal to f and a derivative at t. Now, if we substitute all the values obtained from C and the last phi dash and t is equal to f and t in A, we get the equation A takes the form that a naught t phi n dash t plus a1 t phi n t plus e2 t phi n minus 1 t up to a n t phi 1 t is equal to 0. And from here we can evaluate phi dash n t. Phi dash n t comes out to be minus ant over a naught t phi 1 t minus an minus 1 t over a naught t phi 2 t up to minus a1 t a naught over a naught t into phi n t. Now combining this equation with C, we get phi 1 dash t is equal to phi 2 t, phi 2 dash t is equal to phi 3 t and so on. The last equation, phi n dash t is equal to minus a n t over a naught t phi 1 t minus a n minus 1 t over a naught t phi 2 t and up to minus a 1 t over a naught t phi n t. And from here we get that phi defined by B is a solution of system of equations 2, which we wanted to prove. And now for the converse part, we take phi equal to phi 1, phi 2, phi n be the solution of the system of equations 2. And here we wanted to prove that its first component, namely phi 1t, is a solution of equation 1. Now since phi is a solution of system of equations 2, we have phi 1 dash t is equal to phi 2t, phi 2 dash t is equal to phi 3t, and so on up to phi n minus 1 dash t is equal to phi nt. We get phi nt is equal to phi n minus 1 dash t and phi n minus 1 dash t is equal to phi n minus 2 double dash t and so on. It is equal to phi 1 and minus 1 t. Now, if you compare the first and the last entry and differentiate them, you will get phi n dash t is equal to phi 1 and a derivative at t. Substituting in the last equation of 2, we get phi n dash t is equal to minus a n t over a naught t phi 1 t minus a n minus 1 t over a naught t phi 1 dash t minus up to minus a1t over a0 t phi 1 and minus 1 t, and since phi n dash t is equal to phi 1 nth derivative at t, substituting that value also, we get that a0 t into phi 1 dash t plus a1t phi 1 n minus 1t plus up to so on a n minus 1t phi 1 dash t plus a n t phi 1 t is equal to 0, and this equation implies that phi 1 is the solution of nth order homogeneous linear differential equation. And this finishes our proof. Now move to corollary. Corollary to this theorem states that if f is the solution of nth order differential equation 1 satisfying some initial conditions, then we can make a corresponding solution of the system of equation 2 satisfying the initial conditions. And conversely, converse part states that if phi is a solution of the system of equations 2 satisfying some initial conditions, then the first component phi 1 is a solution f of the nth order differential equation 1 satisfying the initial condition that f at t naught is equal to c naught, f dash at t naught is equal to c1, f double dash at t naught is equal to c2, and f n minus 1 derivative at t naught is equal to cn minus 1. Now let's start proof of the corollary. Now from the theorem 2 we have, if f is a solution of 1, then correspondingly phi given by f dash up to f n minus 1 a derivative is the solution of the system 2. And conversely, also, since this f satisfy the initial conditions that f at t naught is equal to c naught, f dash t naught is equal to c f dash t naught is equal to c1, f n a derivative at t naught is equal to cn minus f n minus 1 a derivative at t naught is equal to cn minus 1. So substituting all these in the solution phi at t naught, we get phi at t naught is equal to c naught c1 c2 cn minus 1. That is phi 1 at t naught is equal to c naught, phi 2 at t naught is equal to c1, and phi n at c t naught is equal to cn minus 1. So now in the next theorem, theorem number 3, we will prove that any combination of m solution, that is any linear combination of m solutions of nth order homogeneous linear differential equation 1 is also a solution of 1. For the proof, we will start with the m solution of equation 1 and we will prove that the linear combination of these m solutions also become a solution of 1. So let f1, f2, fm be m solutions of 1. Now using theorem 2, we get that correspondingly phi 1 given by f1, f1 dash, f1 double dash up to f1 and minus 1 derivative will be a solution to the system. Now since f2 is again a solution of the nth order differential equation, so corresponding to this f2 we can find a solution phi 2 of the system 2, and phi 2 is given by f2, f2 dash up to f2 and minus 1, and similarly for the solution fm of nth order differential equation 1, we can obtain the corresponding solution phi m, namely fm, fm dash up to fm and minus 1 a derivative of the system. Now, using the theorem proved in the class that for the system of solutions, we get that a linear combination of m solution of homogeneous vector differential equation dx by dt is equal to atx is also a solution of dx by dt is equal to atx. So, since this phi 1, phi 2, phi m is a solution of system 2, so we get any combination of these solution will again a solution of system 2, that is phi, which is equal to summation ck phi k from 1 to m is also a solution of 2. And if we write this solution in component wise, we get that the first component of phi is phi 1, which is equal to summation ck fk k from 1 to m. Second component phi 2 is given by summation ck fk dash, k is from 1 to m. Similarly, third component is given by phi 3, which is equal to summation ck fk double dash, k from 1 to m. And the last component of this phi is given by phi m, which is equal to summation ck fk and minus 1 a derivative k from 1 to m. Now, if we take the first component of this phi, namely phi 1, then again using the converse part of theorem 2, we get that this first component will be a solution of the nth order homogeneous linear differential equation 1. And this first component is phi 1, which is equal to summation ck phi fk. And this summation ck fk is a linear combination of f1 f2 fm. And this implies that if f1, f2, fm are solutions of 1, then summation c1 f1 plus c2 f2 plus cm fm is also a solution of 1, and completing our proof. And now we introduce the concept of linearly dependent set of solutions. The m solutions f1, f2, fm of the nth order homogeneous linear differential equation 1 are linearly dependent on the interval ab if and only if there exist m numbers c1, c2, cm not all 0, such that for any point t in AB, c1 f1t plus c2 f2t plus up to plus cm fmt is equal to 0. That is, whenever the linear combination of f1, f2, fm is 0, then the constants c1, c2, cm should not all 0. And if this condition holds, then we say that the set of m solutions f1, f2, fm are linearly dependent on the interval AB. In a similar manner, we will define the set of linearly independent solutions. The solutions f1, f2, fm of the differential equation 1 are said to be linearly independent on some interval AB if and only if for any point t in AB, the combination c1 f1t plus c2 f2t plus cm fmt equal to 0 implies that all ci's are 0. So, now we will prove that how the linearly dependence or independence of solution of nth order differential equation implies linearly dependence and independence of solution of the system, and conversely. So in theorem 4, if we are given n solutions of nth order homogeneous linear differential equations which are also linearly independent, then we will prove that the corresponding solutions phi1, phi2, phi-n of the system 2 are also linearly independent, and conversely. Now for the proof, we first start by taking that this combination C1 phi1t plus C2 phi2t plus Cn phi-nt is equal to 0. And we assume that f1, f2, fn are linearly independent solutions of 1. Now if we open the combination C1 phi1t plus C2 phi2t plus Cn phi-nt is equal to 0, the first component of this combination is C1 f1t plus C2 f2t plus Cn fnt is equal to 0. But since f1, f2, fn are given to be linearly independent, so this combination equal to 0 implies that all the Ci's are 0. And this implies that phi1, phi2, phi-n are linearly independent. Now for the converse part, take phi1, phi2, phi-n are linearly independent. And we will prove that f1, f2, fn are also linearly independent. But on the contrary, suppose that f1, f2, fn are linearly dependent on AB. Then there exist numbers C1, C2, Cn not all 0 such that C1 f1t plus C2 f2t plus Cn fnt is equal to 0 for all t in AB, and we name this equation 1. Now if we differentiate this equation 1, namely C1 f1t plus C2 f2t plus Cn fnt is equal to 0, we get that C1 f1 dash t plus C2 f2 dash t plus Cn fn dash t is equal to 0. Differentiating the equation second time, we get C1 f1 double dash t plus C2 f2 double dash t plus Cn fn double dash t is equal to 0. And similarly, differentiating n minus 1 times, we get C1 f1 n minus 1 t plus C2 f2 n minus 2 n minus 1 t plus Cn fn n minus 1 t is equal to 0. Now combining these n minus 1 equation with the equation 1 and writing in terms of phi1, phi2, phi-n, we get that C1 phi1 plus C2 phi2 plus Cn phi-n is equal to 0 for all t in AB. But because we have assumed the contrary, that f1, f2, fn are linearly dependent and hence C1, C2, Cn are not all 0, and from the fact that C1 phi1 plus C2 phi2 plus Cn phi-n is equal to 0, this implies that phi1, phi2, phi-n are also linearly dependent. But this is a contradiction, so what we have assumed is not correct. This implies that f1, f2, fn are linearly independent. And now we will give the definition of Wronskian of n functions. For any n functions f1, f2, fn, each having derivative up to order n minus 1, the determinant with the first row f1, f2, fn, second row f1 dash, f2 dash, fn dash, and nth row f1 n minus 1 a derivative, f2 n minus 1 a derivative, fn n minus 1 a derivative. This determinant is called the Wronskian of n functions f1, f2, fn, and we denote it by w f1, f2, fn. If we evaluate this Wronskian at any point t, then we write it as w f1t, f2t, fnt, or we can also write it as w f1, f2, fnt. T. So our next theorem, theorem number 5, is regarding the values of Wronskian. So in the theorem 5, we take F1, F2, Fn be n solution of nth order homogeneous linear differential equation 1. And we will prove that either Wronskian of these functions f1, f2, fn is equal to 0 for all t in AB, or Wronskian f1, f2, fn t is equal to 0 for no t in AB. That means either Wronskian is always 0 for every point in the interval, or it will never 0. So let's start the proof. Now let f1, f2, fn be n solution of 1. Then corresponding to these n solutions, we can always write n solutions of the system of equations 2. So we will write these solutions as phi 1, phi 2, phi n. Now, it is clear from the definition of Wronskian f1, f2, fn and Wronskian phi 1, phi 2, phi n that Wronskian f1, f2, fn at any point t is same as Wronskian phi 1, phi 2, phi n at any point t, and we name this equation as 1. Now using theorem 3 of our previous lectures, which I mentioned in the notes given to you on March 24, there is a theorem regarding the value of Wronskian of phi 1, phi 2, phi n at t. So the theorem says that either Wronskian phi 1, phi 2, phi n at t is equal to 0 for all t, or Wronskian phi 1, phi 2, phi n at t is equal to 0 for no t. Now since from 1 we have obtained that Wronskian of f1, f2, fn is same as Wronskian phi 1, phi 2, phi n, so combining with the theorem I stated right now that Wronskian f1, f2, fn at t is equal to 0 for all t, or it is 0 for no t. So moving to our next theorem, theorem number 6, in which we prove the connection between the linear independence of the solution and the Wronskian of the functions. So statement of the theorem is as follows. Let f1, f2, fn be n solutions of the differential equation 1 on the interval AB. Now these n solutions f1, f2, fn are linearly independent if and only if Wronskian f1, f2, fn is not equal to 0 for all t in AB. Now start the proof. Using theorem 4, we get that f1, f2, fn are linearly independent if and only if the corresponding solutions phi 1, phi 2, phi n of 2 are linearly independent. So now using theorem number 4 from the previous notes, in which we have proved the theorem that phi 1, phi 2, phi n are linearly independent if and only if Wronskian phi 1, phi 2, phi n is not equal to 0 for all t in AB. And this holds if and only if Wronskian f1, f2, fn at t is not equal to 0 for all t in AB, because Wronskian phi 1, phi 2, phi n is same as Wronskian f1, f2, fn. Thus, combining the first statement with this last one, we get that f1, f2, fn are linearly independent if and only if Wronskian f1, f2, fn is not equal to 0 for all t in AB. And this completes the proof of this theorem number 6. Now, with the help of the theorem, we will prove a corollary to this theorem, which states that if f1, f2, fn are n solutions of the homogeneous linear differential equation 1, then these n solutions are linearly dependent on AB if and only if Wronskian f1, f2, fn is equal to 0 for all t in AB. So let's start the proof. Now, using theorem number 6, which we proved, f1, f2, fn are linearly independent if and only if Wronskian f1, f2, fn is not equal to 0 for all t. This implies that f1, f2, fn are linearly dependent if Wronskian f1, f2, fn is equal to 0 for some t in AB, and let this t be t0. Then we get that Wronskian of f1, f2, fn at t0 is equal to 0 if f1, f2, fn are linearly dependent. Now, we have already proved in theorem number 5 that Wronskian of n functions f1, f2, fn, either it is 0 for all t or it is 0 for no t. Now, since there is a one t, namely t0, for which Wronskian of these n functions is 0, so this implies Wronskian of f1, f2, fn is equal to 0 for all t. And thus, we get that f1, f2, fn are linearly dependent if and only if Wronskian f1, f2, fn is equal to 0 for all t in AB. Now there is an example which illustrates the above theorem. In the example, we have taken three functions f1, f2, fn, f1, f2, f3, where f1t is t, f2t is t square, f3t is t raised to power 4. And we can check that these three functions are solution of the third order differential equation t cube d3x by dt cube minus 4t square d square x by dt square plus 8t dx by dt minus 8x is equal to 0. You can check that these three solutions these three functions f1, f2, f3 are solutions of this equation. You can check by substituting the value of x as t, t square and t4. Then after you get that these three functions are solution of this differential equation, with the help of the above theorem, you can prove that these three functions are linearly independent on every interval which do not contain 0. How? So take the Wronskian of these three functions. So by definition, Wronskian of f1, f2, f3 will be determinant of t, t square, t4, 1, 2t, 4t cube, 0 to 12t square. When you write the definition of Wronskian, in the first row you have the functions f1, f2, f3. In the second row you have their corresponding first derivatives, and in the third row their second derivatives occurs. So when you take the determinant of these determinant of this matrix, you will get that Wronskian f1, f2, f3 is minus 6 t raised to power 4. And you know that this minus 6 t raised to power 4 is never 0 for all values of t different from 0. So it means that if you take any interval which do not include 0, then on that interval this Wronskian is never 0. I'm repeating. If you take any interval which do not include 0, then this Wronskian of f1, f2, f3 will never 0 on that particular interval. So this implies that f1, f2, f3 are linearly independent on every such interval which do not include 0. And we made this conclusion with the help of the previous theorem we have proved. So I think it is enough for today's lecture. And in case of any doubt or query regarding today's lecture, you can contact me. And I have made a small assignment for you, which you have to submit by Wednesday, that is of 15th of April. So till then, take care and thank you.